Okay, so now what we're going to do is we're going to do our next example problem here. This is going to be example problem 9.3. You're going to want to open up to page 384. And this is going to be a problem that is going to start getting closer to the type of problems that we're going to be, experiencing, like I said, application-wise for our homework. And we're going to be focusing on calculating the bending stress now for the conditions that they outline in our problem. So I'm going to go underneath my camera, and on page 384, halfway down, you're going to find example problem 9.3. Okay. Now, in this particular example, it says it wants us to compute the bending stress. So that's that number we've been looking at, okay? Like using the tangential force, the diametral pitch, the diametral pitches, face width, and then all of those K factors. That's what we're going to want to calculate here, okay? Now it says that we're going to have a setup similar to that last diagram that we saw, where we had the motor with the pinion attached to the gear and then out to the roller. The pinion is rotating this time at 1750 RPM. And you're going to notice that we're going to be driving an industrial saw. This is going to become important to us when we start looking at the conditions that are present. And one of those K values is going to speak to what is that input power. In this case, it's an electric motor. And then the output is going to be this industrial saw. And we're at 25 horsepower. It says the gear unit is enclosed and is made to commercial standards. Gears are straddle mounted between bearings, and the following gear data applies. So they're telling us that the number of teeth on our pinion is 20. The number of teeth on our gear is 70. And our AV number, now this is going to come again a little bit later. This is called a quality number. It's going to be 10. Okay. Don't worry about clicking here, people. We're going to go through. Don't worry. And then over on the side here, I have the gear RPM at 500, and it'll make more sense because our spreadsheet isn't set up exactly the way this problem is, but we'll be inserting it and using it. So let's go ahead and try to kind of fill in that top part and get started, and we'll come back to our problem. So we know that our power is 25, I believe, right? Our input speed off of that motor is 1750. Now our diametral pitch is not given yet. We will be doing that a little bit later. So just skip over that one. Number of teeth on our pinion. The number of teeth on our pinion is 20. And the desired output speed. So again, like I said earlier, many times you're going to actually have an output speed before you know the number of teeth on anything. But in here, they're giving us it kind of in a different order. So I did the calculation, if you would. So our output speed is going to be 500. And then what's going to happen is my spreadsheet is going to give you a suggestion like, okay, notice that the computed number of teeth here is 70. You would go to a catalog then and you would see, is there a 70 tooth gear that I can use? Okay. We're going to assume we can because we're going to continue with this example. And then you would do your chosen number of teeth is, in this case, 70. Okay. That's the number of teeth on the gear. Now, like I said, like we saw earlier, many times this is going to be like a messy number. It's not going to be an integer. And then we're going to have our catalog in front of us, and then we're going to pick what the closest one is. And based on that new number, that's why we have the recalculation down here of many of those values. Okay. So this is kind of like the desired, as it says. And then once we actually pick the gear, then it's going to recalculate for the actual output speed of the gear. All right. So now it didn't fill everything in because we don't have diametral pitch in here yet. So let's kind of see what they're doing in our problem. Okay. So as we look down here, hold on one second. I don't know why I'm forgetting if I actually started recording. Let me go. Let me stop sharing for a second. I am recording. Okay, let me reshare. Sorry. I just wanted to do that really quickly, just in case, because I wouldn't want to do the whole thing over again or not have it here for you. Okay, so now we're here, all right? And we want to determine what the diametral pitch is. We have to put it on top so that we can get the rest of that data down in the bottom. Now, to pick our diametral pitch, we can't just pick it out of the air. We can't be like, I think it will be 10 or 12. We've got to kind of start somewhere. And how we start is we need to calculate what we call a design horsepower. Okay. Now we already have the horsepower that's coming off the motor. That's 25, but that doesn't take into consideration like what's going on after. Okay. And our design horsepower is going to take that power number, that 25, multiplied by what we call an overload factor. Okay. And that overload factor, KO, is something that we have to determine. Okay. Now, KO is going to be found on page 378. I added the page here. So if we go to page 378, Gear Design is paging a lot and looking at charts and tables. And right down here, the overload factor KO is on table 9-1 on the bottom of page 378. Okay. Now, overload factor. This is the probability of a jam up occurring or how volatile or smooth the operation is. So if we have a KO factor of 1, that means that it really has no effect on the stress, no problems. But anything that is, more than 1 now is going to have an effect on that. And the probability of something adverse happening is greater. Okay. So you'll notice that on this chart, we have power source, and then we have the driven machine. Our power source in our case will be our electric motor. So is it an electric motor? Is it a gasoline engine? Is it a turbine? Whatever it might be. Now, to know what a gasoline or an electric motor is, there's 3 categories. There's uniform on the input, light shock, or moderate shock. And to know what category that's in, we're going to go to the top of the next column, and you're going to notice that up here it identifies uniform as an electric motor or a constant speed gas turbine. Light shock would be a water turbine or a variable speed drive, and moderate shock is going to be a multi-cycle engine. So we have an electric motor. We're in the uniform power source category. Okay, so that means when we go down here, we're going to be on this line. Okay. Now we're going to look at our driven machine, our output. In the problem statement, it said that it was an industrial saw. Okay, so we're going to look up here. Down below are going to be our driven machine examples. So uniform is going to be like a continuous duty generator, paper, or film winder. Light shock is going to be fans, low speed centrifugal pumps, and so on and so on. Moderate shock, high speed centrifugal pumps, reciprocating pumps, heavy duty conveyors. It's talking about an industrial saw. To me, it speaks moderate shock. Okay. All right. But in the real world, you'll have a little bit more information, right, about what you expect to happen. So we're going to go under the guise of moderate shock. So that means we're going to go on our uniform line down here to the moderate shock column. And our number there for our KO factor is 1.5. Okay. And that's what the book used as well. All right, so let me get back to our example. Oops, did I go too far? Yeah. All right, I should have my page marked. Go like this. Okay, so they picked 1.5, and now they're going to take that value of 1.5 and they're going to multiply it by our horsepower. So 1.5 times 25 equals 37.5, 37.5. Now, this 37.5 is what we're going to use to determine our diametral pitch. So now we're going to go to another chart. It's in this direction. Sorry. I'm so sorry. I guess not. Where is it? I know what I'm looking. Oh, here it is. On page 377, I'm looking for this chart right here. Okay. So figure 911 on page 330 or 377. This chart helps us pick all of these lines here, our diametral pitches. On the left column, this is our design horsepower. It's the horsepower times that KO factor. So our design horsepower is not 25. It's going to be 37.5. Okay, so we're going to go up, 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 up. We're going to find 30. Here's 40. So just below 40, right? Right about here-ish on this line right here is where our horsepower lies. Agreed? Okay. Now, again, this is kind of an estimate, and don't worry, it's not going to have to be exact. Then what we're going to do is we're going to find our pinion speed. Our pinion speed is 1750 RPMs, right? So we're going to go and we're going to find 1800 and we're going to go just before it. And we're going to go up where it meets that place. So right about here, right? Right about there. So what you'll notice is it's in between two lines, right? So down here is the line for the diametral pitch of 8, and up here is the line for the diametral pitch of 6. So your design, what you want to do, if you pass the 8, then you're too big for the 8. You have to then go up to the 6, even though it didn't hit that line yet. That's where you're approaching, okay? So we're going to put in a diametral pitch of 6, okay? Diametral pitch of 6. Oopsie, I can keep that. Go back to my spreadsheet. So we're going to go back up here and we're just going to simply put 6. Okay. Now, once we know our diametral pitch, we would want to have, in this case, we're using the book's guidance and we're going to follow along with them. But most often you're going to have your vendor catalog out and you're going to know what your, your sizes are and such for a diametral pitch of 6. But we're going with the 20 and the 70. So now that we added that diametral pitch, notice that all of the rest of the fields here filled in, kind of like our kinematic stuff, right? And then also our transmitted load and our center distances, pitch diameters and such. Okay, any questions? All right, so let's go back underneath and continue example 9.3. Okay, so we have now picked our diametral pitch of 6. Okay, so now what we're going to do is you'll notice that it takes time here and it's going to calculate our pitch diameters for both the pinion and the gear. That's going to be found on our spreadsheet C25 and C26. So it automatically calculates this. And remember, you guys did this back in kinematics, right? Now we just have it on a spreadsheet to help us. Now, as we go to the next page, the next thing that they're calculating in this example is going to be our center distance. This also is part of our spreadsheet. So our center distance is the very next thing. So 7.5 inches based on the size of the tooth, that diametral pitch, and the number of teeth that we have on each one of the gears and the pinion. Then we've got our velocity ratio. It calculated that for us. That's in C22 right here. And then the next thing that it has is the speed of the gear. Okay, so based on the 70 number of teeth, you'll notice that we have 500 for our actual output speed for our gear. Okay, so these are done for us. As I move up, it also calculates our pitch line speed for us. Our pitch line speed is going to be in C28. That's down here. Okay, and again, calculations you would have done back in kinematics and in basic mechanisms. And then they did calculate the torque for both the pinion and the gear. Because the stress is not dependent on torque, I don't have it on my spreadsheet, okay? And you don't have to recalculate that. You can see how they got those numbers, okay? And you'll notice that the torque is greater. Actually, you tell me, why is the torque greater on the gear? Why is the torque greater on the gear? Why aren't those the same? We have a 900 for the torque on the pinion. We have 3,151 for the torque on the gear. Why? What happened? There's a longer lever arm due to what? Larger diameter, so that radius of rotation is larger, right? So same force is being transmitted from one gear to the next, right? Tangential force, but we now have a longer lever arm, our radius on that gear. Yeah. And that's why we slow it down. Think about and you guys heard, if you had me, well, most all of you had me for basic mechanisms and kinematics. What was my classic example? I know I mentioned it like at least 4 times. The conveyor at the grocery store, right? That's going to have a motor underneath there, but we can't have it going at 1750 RPMs, right? We want to slow it down so that we can, put it on the conveyor belt and it's not going to fly off. But why else did we say? Even though we didn't talk about it, we didn't actually calculate it there, but it was about torque and doing work, right? Torque is a rotation, it's like rotational motions work. So what did you say? Move the way to the groceries, right? It's going to do work. Work is force over distance. And on a motor that's going really fast, now maybe not an electric motor like this, but if you have one of those spinny toothbrushes, right? They go around super fast. Can you stop it pretty easily from rotating by just biting on it? Yeah. But if it was going slower and it had, you know, more reductions, it gets way harder to actually stop it. So by increasing our torque, that lever arm, we're increasing its ability to do work. And so yes, when we put our case of water on our conveyor, it's not going to, like, you know, stall out on us. It's going to keep going along, right? So so torque is exactly that, right? And that function is because of the physical distance, that radius that we increase from the smaller pinion to the larger gear, right? Cool. All right. And then as we go down here, we get a little bit further down, you're going to notice now we've got our bending stress number. Okay. Now our bending stress number, as we know, is going to take into consideration the tangential force, the diametral pitch, the face width, and that J, which is a geometry factor in all of these K values. Okay. So we already have that tangential force calculated. So that's already right here on our spreadsheet. So we don't need to be worried about calculate that. But what's good to do is to just double check that you've got answers that are relatively close. So if we look, we have 540.23 and they have 540.3. So again, a little bit of rounding error, but we're gonna say we are on top of it. Then you're gonna notice that they also calculate the radial and the normal force. In our case, we're not going to. Again, it doesn't speak to the final stress that we're interested in. So we're gonna bypass that for now, but it's good to know. Okay. Now the next thing that we're gonna input is gonna be our face width. Okay. Our face width they have here at 2 inches. Again, this would be dictated by the vendor we would get our gears from. So in this case, we're gonna go with what they have. So at the oopsie. At the top of the next section where we have face width, the secondary input information, we're going to put 2. Okay. And now notice that I calculated a face width ratio of the face width to the pinion diameter. And over on the right-hand side, this is a condition that we have to meet. So notice that we need to be between 0.5 and 2. If we're outside of that range, then we've got to adjust things up on the top. But we have 0.6, so we're totally fine. We can keep going. Okay, let's go back to our spreadsheet. I want to follow along with that. So that's going to be our face width. Now, the next thing we're going to input is going to be our JP and our JG. These are those geometry factors. We're going to go to page 376 and we're going to look at figure 910. Now, there are 2 figures on this page. One of them is for 20-degree pressure angles, which is the top, and one of them is for 25. We're going to focus on the top because we are 20-degree pressure angles. Now, to find the geometry factor J, which is going to be on our vertical axis, okay, we have to know if we're on our pinion or our gear. So we're going to start with our pinion. Our pinion, we're going to find the number of teeth for which the geometry factor is desired. So how many teeth did our pinion have? Was it 20? 20, okay. So notice that we have a line here, and this is where 20 number of teeth is, okay. And then you're going to notice that we're going to align it with the number of teeth on the mating gear. So our pinion is 20 and our gear was 70, right? Okay. Now this is the trick. Not to get your eyes to cross. So now we need to be, you notice that they have a 50 and they have an 85. So in between those 2 lines and a little bit closer to the 85 is where we want to, I got to count this 1, 2, 3, 4. So this is going to be 1, 2, 3, 4. So right about there and over. Okay. Right here is where I would read that number. Now notice that there is some judgment here. You kind of see how you would go up in the middle-ish here. And again, I counted 1, 2, 3, 4, 4 sections up, 1, 2, 3, 4 sections up. It happens to be on this very line. Okay. Is where I got it. Okay. So now if we look at our number, that would be 0.3. 1, 2, 3, 4, 5. So 0.33. Is that what you're getting for your J? Would you agree about? So let's look what the book decided to do. Is we're going to make our numbers match. It's going to be close, but there is some, you know, little bit of error here. So 0.335 is what they got. Okay. So we're going to put that into our spreadsheet, but know that when you're reading it, do your best. Okay. And just kind of come as close as you can. So I'm going to go back to my spreadsheet here and I'm going to put in 0.335. Oopsie, not there. My JP is right here, 0.335. What was that? Oh, thank you. You're right. For the red, page 376. Wonder who did that. Thank you. All right. Now we're going to do the same thing for the gear, but this time on that horizontal bottom axis, we are going to use the number of teeth on the gear this time. So going back, number of teeth on our gear is going to be 70. So right between the 60 and the 80, right? Okay. And then the number of teeth on our pinion is 20. So it's just above the 17, right? Just above. So there's an actual line there. I'm going to go to that line. Now, not nice what they did. You got to go. I need a piece of paper, I think. You got to go through that little illustration there to get over to our number. So I think that's pretty good. Okay. So notice we're at 0.41. Okay, that's what I would read off my chart. I'm at that next line, 0.41. Okay. Do you see that? So you're going to come over right here. I'm right there. So 0.4, and then I'm to the very next one, 0.41, because it would be 0.41, 0.42, 0.43, 0.4, 0.45.
How did you get to that?
70 on our gear between these two. This is for the gear. Yep. Same chart. Yep. But now remember this axis is for whatever gear you're calculating or determining the J factor for. So your gear now is going to be down here. So 70 and 20. So this is going to be above the 17, kind of closer. So I got to that line. Let's see what our book decided to do. What was it? 0.42. Okay. Yep. Then let's use their numbers so that our numbers come out closer. So again, there's a little bit of judgment. Okay. But do your best to be as accurate as possible. All right. Now we're going to continue to follow now we're going to be skipping over some things here because the things that we're skipping over are going to pertain directly to like pitting stress instead. So these are all kind of together in here. So they're pulling out for this example. We're only worrying about the bending stress. So let me go back underneath here. So we've got our two J factors. The next thing we're going to do is we're going to input our overload factor. We already looked at that. We know that to be 1.5. So KO is down here. Oopsie, 1.5. Okay. Our next one is our size factor. Okay, our size factor. So you'll notice here KS is our size factor. We're going to go to page 378. Right. At the bottom of the second column is the suggested size factors, KS. Now, they are based on what your diametral pitch is. So anything that is greater than 5 is going to be equal to 1. Okay. And we're in the diametral pitches, not the metric. We're in the diametral pitches here. So ours is 6, which is greater than 5. So, and including and equal to 5 is going to be 1. So our KS factor is going to be 1. And that's what they have here for their example 2. So we're going to put it into our spreadsheet. Now, the next part that they look at is ultimately going to be what we call our KM factor, and this is called the load distribution factor. To calculate our KM factor, we need two factors that we have to read off of charts. We need to read off the CPF, okay, and the CMA, right? So we're going to go over to page 380. Oh, I'm sorry, on the bottom of page 379 is where it starts. So our CPF is at the bottom of page 379. Now, to get this, we need to know what our face width is, and then what our face width to our pitch diameter ratio is, okay? Our pitch diameter, or I'm sorry, yeah, our pitch diameter ratio. So our face width to DP was something on our spreadsheet. So that was right here. It's 0.6, okay? So then what we're gonna do is we're gonna go back to, and then we also need our face width of 2. So 2 on that horizontal axis and 0.6 along the line. So I'm gonna go underneath here. I'm gonna find where 2 is. So you'll notice that this is number 5 and this is the face width in inches. So 2 is gonna be the second line from the 0. And then here we have, it goes from 0.5 to 1. So it's gonna follow that line along, but then just a little bit above, okay? And then over, all right? Now, if we look here, it's between 0 and 0.05, right? In between there. Let's see what our book picked. I think they have, 0.04 or calculated. They did the calculated value as well, 0.047. Okay, so I'm going to put in the 0.047 because it gives us an extra decimal place, but 0.04 reading it off the chart would be totally fine. So we want to find this value of 0.047, okay, the CPF. Now the CPM on the following page at the top is where we're going to read that value. So that's going to come on page 380. Okay. And this one is going to read from the face width again, but then we have to pick what our situation is. And if I recall, we are a commercially enclosed gear unit. So let me just verify that that was in our problem statement. It's a gear unit is enclosed and is made to commercial standards. Yep. So that is going to be the one that we're going to use, that line. So we're going to find our 2 again and where it crosses with that third line up, 1, 2, 3. So here-ish. So 0.155, 0.16 is probably what I would call it. Commercially enclosed gear units. That was in our problem statement. Yep. Mm-hmm. So if I go back over here, oopsie, I wanted to actually first look in my problem, see what the book picked so that we line up with them. They did, 0.16. Yep. So that is exactly what we got. Okay. So now by having these two values in here, it automatically calculates now my KM factor. Okay. So you don't have to pick that one off. You just have to pick these two off of the chart to feed into that. All right. The opinion. Oh, is it not? Yep, it should. It should. Let me see here. Does that look better? Yeah. Yeah, go ahead and change that color if you need to. Okay, so then let's go back to our problem and see where we're at. So we did our CPF, our CMA, calculated our KM, right? And then now we're ready to put in our next factor, which is going to be the rim thickness factor. Now, rim thickness factor it really comes into play when we get larger gears where we end up having like spokes, okay? And they take material out because it's just, they get too heavy and oxy to kind of, maneuver around. So in our case, we have smaller gears. We're going to assume that they're solid because it doesn't tell us that they're spoked. So whenever they're a solid blank, then we're just going to use the value of 1 for KB. And that's what the book uses here. So we're going to put a 1 for the KB for the pinion and 1 for the gear. Okay. Oops, I've got some other things filled in here.
Are we gonna ever have to use that?
If you have a spoked gear, yeah. Then you would have to go to the chart. The what?
That shows that chart, on that chart, it has the back of for each code. Oh, never mind. Missed it. Never mind.
Oh, okay. All right. Okay, so let's get back to our chart. So we've got our KB factor. Now we're going to go KV. So KV is our dynamic factor. And this is going to have to do with our pitch line speed and how accurate our gears are. This is kind of like how much vibration or how little vibration we're going to have in our gear set. So so we're going to go to does it give us a figure? I don't have the page number. I was trying to put the page numbers down. So we're going to go to figure 916. And that is going to be on page 383. And you'll notice there are 2 charts here. The top chart is in English units, feet per minute, and the bottom one is in meters per second. Okay, so in metric units. So we're going to go to the top here. Okay, and our pitch line speed, we're gonna find, was on our spreadsheet. I can look back on there. Our pitch line speed was 1527. Okay, so if we go here and we find where 1527 is, so we have 1,000, 2,000, so 1,500 is right in between. And I'd probably stick pretty darn close and a little bit to the right of that line. And then our AV number. In the problem, it told us that our AV number, our quality number is 10. So you're going to find that line here and you're going to line it up with about 1,500. And you'll notice that when we read it over to the left, our KV factor off of that chart, what I read is 1.4. Okay, 1.4. So I'm going to go back to my problem. I'm just going to see what they put in. And they read it even more accurately, 1.41. Okay, so I'm going to use 1.41. And again, when you do yours, if you leave it at 1.4, it's totally fine. So that's my KV factor, 1.41. Okay. Now, as we look back at our equation for calculating our stress number, I'm going to go back underneath here. So right here on page 385 in our problem, here is that equation. So for the bending stress only, we needed the tangential force and we needed our diametral pitch. We divided by our face width. We got our J factors for both the pinion and the gear. And then we just now added all of those K factors as they apply to the bending stress. If we didn't put something in, that means that it's gonna apply to the contact stress, okay? Because we didn't fill in all of the lines yet, okay? So as we look to the bottom of our problem here now, you're gonna notice that we have 2 stress values. The first one is going to be the stress on the teeth of the pinion. And the second one is going to be the stress on the teeth, bending stress on the teeth for the gear. Okay. So let's go back to our spreadsheet and see how we did. So you'll notice as we go down here, there's still some more things to fill in. You'll also notice at the bottom of the chart here, I have a section for bending stress, a section for pitting stress. Okay. Now, even further down, there's an adjustable allowable. Don't worry about those just yet. We'll talk about those, but don't worry about these down here. The only ones we're worried about are the 2 that are here that we're comparing back to. So you'll notice that our numbers aren't exactly what the book has, but they're pretty darn close. And we used all the same numbers. So we get 12 on the spreadsheet, 12,350. And then they get 12,376, but all of our numbers are exactly the same. So I'm not exactly sure where it is, except possibly they're rounding their 540, their tangential force to 540, and we have ours, from our spreadsheet, which isn't rounded. And then the gear value here, they get 98.71, we get 98.51. Again, their tangential force appears to be rounded, ours isn't, so I'm thinking that's probably where it's at. So so these are going to be the numbers then for this practice problem. So I know it's a lot of reading of charts and going through, we're going to continue to get practice with this, but at the moment, does anybody have any specific questions kind of about, what we filled in? Was there anything that you're like, why did we do that? Or why did we, how do we get those values? The J's and the K's are all from the charts, and they, remember, speak to our design, because every design is going to be a little bit different. They're going to have some different conditions. They're going to have some different sizes, and that's where we can capture that in those variables. Okay. All right. So for this practice problem then, all right, this is practice problem. If you wanted to put it at the top here, this would be example 9-1, or I'm sorry, 9-3. Okay. And what you can do is, gosh, it's going to be a little tiny, isn't it? But I should be able to see it by zooming in. So just kind of get enough in here. If you wanted to do it in maybe 2 screenshots makes sense. And then make sure you get your top and your bottom so that I just need to see, to the bottom of where this stress is, everything else above, because I want to make sure that you have those values in there. Now, did everybody have success with the numbers matching up to what we have here? Yeah. Okay. All right. So now what you want to do is you want to add that screenshot or two to your practice problems document where you have your other screenshot from the previous example. And this will be then, like I said, it's kind of like a participation grade, if you would, making sure that you're following along with the stuff that we're doing. And we're always doing these during class. I check these for completion. I am not, if I don't see something that's quite right, I might, note it, but it's either you did it or you didn't. Okay. Yes. We didn't do a random number. Well, I'm assuming you're reading it off the chart because you're going to be using the tables that are referenced. That's how you have to get it. Yeah. And so just read it as accurately as possible. Yeah. And that's why following along with this example, making sure that okay, if I can get my number nice and close to what the book did, then I know I'm reading the chart correctly for their conditions. So then you can apply it to, if it's a different number for your next example. Does that make sense? Yeah. Yeah, it is reading off of charts. And you got to be accurate. And you got to kind of take your time and make sure that you're seeing what you're supposed to see. Okay. So that's why the practice with the examples, making sure that you can line it up. And if yours matches theirs for what they have, then you should be able to then cross over to your application when it's different. Okay. Yeah. All right. So that's, we're at 3:30. So we're normally done. I guess we're here till about 10 till, right? So, so this is probably a good breaking point. So the next time that we get together, we'll continue on and, continue doing some more examples and yeah, and probably also getting started on some of that homework that you guys have too. Okay. So I think we meet in 2 days, right? So today's Tuesday, Thursday will be the next time that we meet. Okay. All right. Then what I'm going to do is I'm going to stop sharing. I'll stop recording.